Hello, I'm Dan Sweeney from MathSpec Incorporated. In this video, I'd like to describe 5 MathSpec functions that are available in the Excel add-in. The 5 functions are mass, which finds the exact mass based on a formula; rings and double bonds, which calculates the rings and double bond equivalents; IsoCalc, which calculates the isotope distribution; Plaus, which finds the relative frequency of a particular composition, and it's based only on the heavy atoms; and Hyperlink, which generates hyperlinks to Pubchem search. Now, the Excel add-in only supports 9 elements, and it's the same with these 5 functions. The elements are listed here, and these are the most common elements. The functions work either with a cell position, like you could type in mass D37, or you could type in an actual string formula. If you use a string, you have to put quotation marks on both sides of the string so Excel knows that it's a string. You can also do calculations with these directly. So for example, you could subtract the mass of D37 from whatever the mass is in D23. For purposes of illustration, I'm going to use Pubchem compound 60807. The accurate mass fragmentation data has been published for this compound. The isotope ratios of the molecular ion have not been published, so I'm going to use theoretical data for that. So here is the accurate mass fragmentation data. The compound has a molecular weight of 499, and this is its positive ion data. The isotope ratio numbers, which are theoretical, are put over here. I'm using all the default parameters, except normally fluorine is set at 0, but in this case I'm going to clear that out so any value for fluorine will work. The default parameters below are 3 millidaltons for the air window, 9% for the isotope ratio, absolute air, and the formula restriction, which is based on the Plaus function or plausibility, is set at 1. Now, I've already transformed this data for the sake of time. If we bring up partition 1, these are the assignments, if you will, for the subfragments. The score is 102. Partition 2, again, it's doing a good job of assigning fragments, and it also has a partition score of 102. Now, partition number 2 has only 2 formulas possible. Partition 1 has about 15. One reason is this has 4 subfragments instead of 5, like number 2. So some of these fragments are fairly large, and it's harder to pin down the elemental composition. For the sake of the demo, I'm going to focus on partition number 2. The first function I'm going to try here is mass. So I'm going to type equal mass D37, and that will bring up the mass of the formula here, C4H8O2. And because it's Excel, we can pull across and fill down also. So all of these subfragments, except subfragment 2, have exactly the same formula. If we want to look at how close these things are to the calculated mass from the data. That's in row 23. So I can say minus E23 and also I can multiply it by 1,000. I like millidaltons. And I'm going to put dollar signs here to make that an absolute position. $1,000. So it's about 1 millidalton off, and I can pull that down also. So that the first formula is only off by 1 millidaltons, and the second one is off by 2.2 millidaltons. We can also look at the rings and double bond equivalents, and usually this is more useful than it is for the entire molecule. It can be used to help decide how the cells are arranged. Now, if there were multiple alignments possible, there would be an arrow here. So these cells, these subfragments, are all connected to the white subfragment, and that's the only alignment that worked out. Now, if I see a zero, some compounds, like for example, if we had an ethanol here with 0 rings and double bonds, we know that ethanol cannot connect to 4 other subfragments, so that would rule it out. Now in this case we have a nitrogen and 2 oxygens, and since it's saturated it could be 2 alcohols and a primary amine, let's say. So now a nitrogen can connect to 2 subfragments because you could have an NH2 and each of those H's could be displaced by another subfragment. So we can't rule out either one of these formulas based on the rings and double bond equivalents. So now let's look at plausibility. And this will give us some idea of how common these particular molecular formulas are. Now, plausibility in this case, for example, C7, it's just looking at the heavy atoms, so C7NO2F, and this is the most uncommon. The other formulas are very common. So, for example, C4O, there are a lot of compounds that can be divided into subgroups where some of them have C4O. A 9 is not that unusual, so we certainly wouldn't rule it out. If it was a 1 or a 2, we might say that it's not as likely as the other set of formulas. The next function I'd like to describe is the hyperlink. Okay. What this does is set up hyperlinks to Pubchem, so if you decide you want to search a particular formula, you can do it very easily. And in this case there's only 2 sets of elemental compositions, but for example if we were doing the first one, there's 15 different formulas, so you might want to look at a number of those to see what kind of compounds would fit that formula. So if I click on this, it will fire up Pubchem and do a search on that formula, which I then recommend that you sort by CID number. And so if we look at these are all compounds with that formula. Go back, and of course in this case it is butyric acid. That is the actual subfragment. And let's see what some of the others are. Isobutyric acid, 3-hydroxybutanol, propylformate, ethyl acetate. Now it has to be, in the case of ethyl acetate, you're talking about attaching it to another. The second subfragment has all of these attached, and ethyl acetate really doesn't have any place to attach. Now the last function is IsoCalc, which will generate the isotope ratios for a formula. And in this case, these are already calculated. The first four are calculated as part of the results file. Now I'd like to briefly mention how the Plaus values were calculated. The idea behind this is that when you have a formula such as sucrose here, C12H22O12, if you're working on a fragment or subfragment of that formula, there are more possibilities than are actually possible. In other words, this would be a very logical subgroup of sucrose. But C2H6O7, it's also a subset of this formula. But what's the chances of having 2 carbons and 7 oxygens? So basically, to get some idea, 70,000 common compounds in the molecular weight range between 350 and 550 were partitioned through systematic bond disconnection into sets of 4 subgroups. And then if the heavy atom composition was less than 250, if the mass of that subfragment were less than 250, then it was saved and recorded. And only once would it be recorded for each compound. So the maximum count, if there was a subgroup that was found in every compound, you could get a count of 70,000. Now if you look at all the combinations of these 8 elements, because hydrogen is not included here, there are over 8 million combinations. But now this is of course ignoring the fact that you'd have to have compositions that will connect to each other. But of the 8 million, only 37,591 compositions were actually found in these 70,000 compounds. And if you look at how many times each was found, most of them occur very infrequently. So, for example, about 40% of the compounds occur less than 4 times. Now, the most any composition, heavy atom composition occurred was C2, which is ethyl or ethylene, which occurred 67,000 times in the 70,000 compounds. I should mention that once the Excel add-in is activated, these functions are all available in any Excel spreadsheet that you're using. So you don't actually have to do partitioning to activate these. Thank you.